All right, next on the list is hydrates. So hydrates are the reaction of an aldehyde or ketone with water. Um, and essentially, the water has a partial minus, carbonyl carbon still has a partial negative. So theoretically, this could happen. So we would have the water add in there. That would form this high energy species, and then a proton could transfer to produce the hydrate product. But would this be a very favorable reaction is something we should be asking ourselves. And how do we relate that to things we've learned about before? Well, there's that thermodynamics equation, delta G equals delta H minus T delta S. So what was this all about? Delta H was the bond energy variable. So essentially, are we forming more stable bonds? If so, then that would be a favorable thing. Delta S was the entropy situation. Are we generating something more or less random? More randomness is more favored. So as far as hydrates go, it turns out that, I guess, take a minute. What do you think? Do you think this is an entropically favorable or unfavorable process? Entropically, so delta S. Yeah, so delta S, we are going from two molecules to one molecule. Two things are more random than one thing. So this is entropically disfavored. So we want more randomness. We're getting less randomness when we go forward in this reaction. What about the hydrate formation is blank neutral? That's talking about the delta H term. So essentially, enthalpy, we've talked about the strength of CO pi bonds. Usually sigma bonds are stronger than pi bonds, and a CO sigma bond is, we have an extra CO sigma bond here, but that was at the expense of a CO pi bond, and CO pi bonds are pretty strong bonds. In reality, enthalpy is a little bit favored in the forward direction here, but not enough to overcome the disfavored entropy of the product. So usually, we're going to make a bigger arrow here. Usually, hydrate formation is disfavored, but we're going to talk about a few things. So does the equilibrium over here? Usually the equilibrium's over here, but we are moving into talking about a few places that's not always the case. But that's what a hydrate is, and it can form, and depending on the given electrophile, the given carbonyl compound, it does form, and we'll see that soon. So when are hydrates favored? Hydrates are favored when the carbonyl is particularly electrophilic. So electrophilic, I'm just going to put E+. Given that, we have three different carbonyls up here. Which of them is going to favor the hydrate the most? A, B, or C? So take a minute, think about that. Which of these is the most electrophilic? That's going to have the most hydrate formation. And then unpause. All right, you did that. Great. The bullet point on your course packet, more sterically accessible, blank electrophilic, blank hydrate. So if something is more sterically accessible, it's more electrophilic, and there will be more of the hydrate. So this just has two hydrogens around it. That's going to make this carbon really accessible for a nucleophile to add to. So this would be the most electrophilic of these three. Turns out that this molecule is about 99% hydrate at equilibrium. So we can see that when something is extremely accessible sterically, it is forming more of that hydrate. What about the least accessible sterically? This is acetone. This is formaldehyde. Acetone is only 0.2% hydrate at equilibrium. So even if we just get two CH3s right around that carbonyl, they are enough to really disfavor the hydrate formation. This is in the middle. It's 58%. So we see that the steric accessibility of that carbon is really important for how much hydrate is formed at equilibrium. How about these three? Which of these is the most electrophilic? So take a minute, decide, make your selection, and then come back. All right, you pause it, you're back. So this blank on the course packet, larger blank on the carbonyl carbon, blank electrophilic, blank hydrate. So electrophiles are positively charged, so larger partial positive on the carbonyl carbon, more electrophilic, more hydrate. A CH3 group, like that one there, is electron donating. So that is going to make that carbonyl carbon less partially positive. What does a Cl do? A Cl does induction, right? It pulls electron density toward it. There's a partial minus there, partial positive here. And induction, that partial positive gets transferred down the carbon chain. So there's that size partial positive here, that size partial positive there. What about this one? This one has 3 of those chlorines. So each of them would have about that same size partial negative, but that means that collectively the partial positive on the carbon is going to be much larger, generating a much larger partial positive on that carbonyl carbon. So the actual numbers for this are not clear. We don't know what percentage these two would be. We know this one's 58% hydrate, like we talked about in the last segment. But which one is this going to be greater than or less than? This is going to be more electrophilic, so there will be more percent hydrate. So we'll just put an arrow that way and say increasing percent hydrate. So as there's more partial positive, more percent hydrate. So that is how hydrates work.